that the certain field is symmetric, it has dipole offset polarity that of the opposite that of the Earth, and the tilt is almost parallel. Then Voyager data, Voyager 2 also confirmed the findings of Pioneer. Then combined on this data from Voyager 1 and 2, the Z3 model comes up. And in a simple way, this Z3 model, the model is simple in the sense that it simply said that this magnetic field is as simple as a three spherical harmonics. These are the three spherical harmonics which found out to be the values. I think the values are not so important, later on we will realize. Then the magnetic field is given to be 0.84 Gauss solid, very small. These are the findings of the magnetic field. Just to make a visualization of what is meant by symmetric. That certain ring, if you realize, see, there is a perfect symmetry is there in both the left and right hand side. That looks like, and here I'm comparing with other planets. Just again, this what is meant by offset. Here, if you look at the center of the dipole given there, in certain it is displaced a little bit up, whereas in Jupiter the orientation also is there, but it's perfect. Then the Earth, all those. This is the meaning of offset. And why I'm telling all this, because later on it will have effect on understanding of the interior of the planet. So I'm just emphasizing here. Then again, Pioneer, Voyager 3, all the three data, the data from three spacecraft were combined as SPV. Here also, it's again confirmed the finding of Z3 model, except the Gauss values here, the Gauss coefficient, the spherical harmonics are. Now, what is the meaning of this Gauss coefficient spherical harmonic? How does it can be applied to the study of planet? That is the meaning of there. I put that picture just to have a mental picture of what a Gauss coefficient looks like. Now here Z, LM, the subscript give us the the division in the latitude, the Z, whereas on top of the postscript, that 0 give us longitudinal division. So see, if you see, we get the term only of 1, 2, 3, whereas the rest of the terms are 0, 0. That means that the symmetric, as I had shown before, see, if you look at perfectly, there is no division on the vertical side of the planet. The magnetic field in the vertical direction, whereas in this, if you look at Uranus, there is so much non-symmetric terms, and the divisions are, it's almost like a cloud. But in this perfect alignment is the most challenging, because there is a theory in in electrodynamics, there is a theory that if a magnetic field is created by dynamo action, then we cannot get perfect symmetry. That challenges it was in 1903. A constant asymmetry magnetic field cannot be maintained through dynamo action. But then, if we don't say that this magnetic field is produced by dynamo action, then we have no other. We cannot simply say that, okay, this magnetic field is the outcome of a charge movement. No, if it is a charge movement, if it is horizontal, but in the case of planet, we expect it to be circular. And once it is circular, hydrodynamics production of magnetic field is nothing but a dynamo action, or we call it dynamo theory. So this becomes challenging. Then the observation says that that if I show you once again, if you look at that, it has no asymmetry. So it's perfectly symmetric. It's almost like we have a dipole in the lab which is perfectly symmetric. So those things become challenging to the limitation. So far, even after 3 spacecraft visited, we were unable to understand what is this. Then here I just put it as, does it has non-symmetric component? Till now cannot be answered. I'm saying this again to give the message that the study of this is still very relevant. Someone can just if anyone is still interested in the planet Saturn ring, there are so much to study about that. So I would like to emphasize that, right? I put it this. Then how is this magnetic field generation? How is this dynamo action? What is the mechanism inside this interior of the planet? That was given by Stevenson in 1980 and 81, which later on becomes the discussion till 2022. There was a paper by Yadav, Indian Bond, that he argued about this. According to that Stevenson theory, it says there is something called the planet interior is divided into layers. And why it is divided? Because of the pressure, around 2 millibar and temperature around 10 to the power 4 Kelvin. That hydrogen metallized to form what we call metallic hydrogen. And once that happens, this helium cannot mix anymore with the helium. Therefore, the helium's due to gravity, it goes to the center of the planet, and thereby forming a layer inside that inside of the planet. And because of this layer, temperature gradients is formed. That is the north, the south temperature difference. And because of this temperature gradient, then there is a thermal wind, and that thermal wind try to move the particles and thereby creating the magnetic field. That is in the gist of what is meant. Now, if we say that magnetic field is produced by the movement of the charged particle, here we mean the charged particle is helium mixture and then helium and hydrogen mixture. They are separate and then mixed depending on the layers. If that is the case, then how do we explain this perfect symmetry, almost perfect symmetry? The rotation, usually in the case of the Earth, we have around inclination of around 17 degree and 23 degree, because the magnetic axis and the rotation are different. In almost the planets, they are not coincident. But in the case of Saturn, it is almost perfect. Later on, in 2002, it is even discovered that it was thought to be 0.07 degree. That means almost perfect. But it may be even smaller than that. That means almost perfectly parallel. That is the one. Now, as I said before, this becomes challenging for any dynamo theory. Now, but if that Stevenson proposed that this is the case, then how does it explain? Now, his explanation was that because there was a different layers, because of the different layers, now the thermal winds produced, and because of the thermal winds, now the charged particles are moved here by creating the magnetic field. But in the process, because they are different layers, when the magnetic field pass through these different layers, the non-symmetric part are suppressed, and thereby we observe the symmetric part outside of the planet. That was what his explanation is. That means initially in the production of the magnetic field, we have a non-symmetric part as well as symmetric part, but the non-symmetric part are suppressed outside of the planet. That was his explanation, and till now this becomes the topic. Some said yes, he's true, some said no, this and that. So some of us can join in the discussion and then do some research on, say that okay, this should be the real one, we can discuss it. There are several papers which I have not highlighted. The merits of Stevenson is that there are another observation of a certain light, the helium, the calculation of the helium which is expected, that one is less, whereas the heat, for example, the heat received from the sun, if it, and the heat radiated, 3 times it radiates, then the amount it received. This is what we call excess luminosity. If sunlight gives, let's say 1%, it gives back 3%, something like that. That is what we call the excess luminosity. This was able to explain. So then I'm just giving again here the pictorial representation of what is going on inside and how the inner core of the Saturn is divided and how they create the magnetic field. Then the limitation of this model are many. It explained 3 of them, but the limitation and discussion it gives for modern days. If you go through, one of them is that it does not tell us where exactly is how much is the differentiation. That means the division of the layers does not tell anything about this. Then where exactly is the dynamo region? As per the calculation, it should be little bit 0.05 of the equatorial of the planet, but exactly does not tell. All those are still unknown, and some studies are still continuing on based on the Cassini data. Cassini data collection ended in 2017 only, September 2017. Till their data collection is there, and even till now, data collection, interpretation of the data is still going on. So in this year up to 2022, it was this one is very recent, this year only. Then these are the points against Stevenson. Whereas there are also so many studies which support this. I think we will not discuss all those things. The discussion and conclusion so far is understanding of the whole process of the generation of certain internal magnetic field is still an open question. That means we still have to work on this. Those who are interested in the planetary rings, we can work on this. This is one topic. And another thing is how exactly this, he simply said that the non-symmetric components are suppressed, but how exactly does not explain. Then what do you call now? Another study is that whether the magnetic field remained constant throughout during the Voyager area, Pioneer, and till now. Is it fixed? Some said fixed, some said it varies with time. There are support and against. So nothing exactly is there. Therefore, what we call based on the Cassini data, there are other new models coming up, but later on they have the same conclusion except the calculation of this Gauss coefficient. Then I simply put as asymmetry 1, 2, 3. These are nothing to worry. The names I simply put it by myself to categorize the model because there are so many models that they are different models, almost similar calculation, but the values of spherical harmonics, all those calculations are differently. Then we have the Cassini 3 model. This is based on the initial Cassini model, which we expect because Cassini, it flew to the certain more closer and with more different angles. It collected data from all the 3 dimensions. So expected to be giving us some more detail. Based on that, this certain magnetic field, nature of certain magnetic field was again modeled. Here, the till C, it found the till which was supposed to be less than only 1 degree. Now it's it come about 0.06. Whereas here, this Cassini model 3 was able to tell the thickness, the expected thickness. Then here, see, this is one, the Cassini 3 model find that till now there was no information about whether there was a change in the magnetic field or not. Or is it the magnetic field constant? That also, if it say yes, there are another question. If it say no, then there will be question. Those things are there. So we need to know whether this, why we need to know, this is important also because if we are studying charge dynamic, and we need to know whether our magnetic field is changing or it is not changing. Now, if it is a changing, we have different equations. If it is not changing, then different equations. So we need to analyze because we are studying about the ring materials, and this becomes important. And here it says Cassini 3 and 5. It says there is indeed variation. For the 32 years, within the 32 years, there was a variation in the magnetic field. And those variation, the value, of course, it's very small, 1.2 nanotesla only per year. It changed a little bit, but the magnetic field changes. But later on, we will find that in 2021, this Kimberley, they reanalyze all this and find that they said that the magnetic field changes. It's just because of the choice of their model. That means their modeling technique was wrong. So that means the debate is still on. They said there are changes, and so now in 2020, last year, somebody said no, it does not change. So argument is that it's still relevant, this study. So then this one, this is the grand final Cassini, where the same Cassini took what you call crush itself in the Saturn. That was just they crushed in the Saturn atmosphere. That is to avoid the what you call the nature of the atmosphere of the ring. They did not want to disturb the ring particles. Therefore, they made Saturn, the Cassini to land in the atmosphere and crash. That's the reason. And during those, it passes through the rings. See, till Voyagers, Pioneers, when it goes to the planet, it just gates around the surface. But the Cassini, the advantage is that it just goes between the rings up and down. Before, we never realized that we can go through the Saturn rings, by the way. We thought that But this Cassini proved that between the rings we can go, come up. So in the way in between it collected data, and then so that is expected to be more correct. And based on that, now before, if you remember Z3 model, SP3 model, and the Cassini initial Cassini, which I call 3 and 5, we can find only the spherical harmonics up to Z 3 times. But here, because of it now, Cassini 11 model was able to give up to a 14 Gauss coefficient. That means, if you still remember that the picture here, that means it is able to give more information about the latitudinal difference of the magnetic field, the difference in the latitude. As we go latitude, what are the difference? So these are the terms which give us the magnetic field. Then more recently, the latest 11 plus model, which is, okay, that bracket, I think I deleted something that it has nothing to be worried. So now reanalyze and then find spherical harmonics, which are now spherical harmonic which are more than what the Cassini 11 got. And then now the dipole till was estimated to be less than 0.07 degree. Those are the new findings. The discussion again, from here what do we learn? None or all of the models could fully describe its characteristics or tell us the exact nature of the magnetic field. So even after the Cassini, we are unable to tell what exactly is the nature of the magnetic field. We are not sure yet, even till now. Then what about the models? There are around 15 models trying to explain magnetic field observation, but still, none of them could explain all the characteristics or reproduce the findings. Now, before, when we try to analyze, does it has a non-symmetric component? Does it vary time? We did not know, but we are able to tell now, yes, based on whom you support. Based on whose studies you support, you can say yes. Then based on whose analysis we support, we can say no. That means the argument is still on, and we can join the argument if anyone is interested. We can study the ring matter. Then discussion and conclusion. Understanding of the whole process of the generation of certain internal magnetic field is still an open question. Now that means conclusion of this also give us a challenge. Now, if we are not sure what the magnetic look like, then how do we study the charged particle dynamics, and how are we going to study the ring formation, or the what you call the life of the ring of certain rings. Then any studies involved, so our conclusion is any studies involving magnetic should incorporate both the asymmetric and symmetric. For now, if somebody wants to study the charge dynamic, then he might have to concentrate to one. We will assume that the magnetic field is asymmetric, and another studies has to be again on non-symmetric, because we are not sure yet whether it is asymmetric or non-symmetric. Whereas in the case of the planet Jupiter, it's already, whatever to be found, the nature is already found. But in the case of Saturn, we are still unclear of whether it is symmetric, non-symmetric, even if it's symmetric, and how does it look like. Then whether it changes with time, I mean, is it a varying magnetic field or not varying? Is it time varying magnetic field? Or that also we are not sure. That means anything we study, it becomes more challenging, and this are the findings. Thank you, that's all.
Okay, thank you for your review talk, and quite informative. Okay, it's now open for discussion. Yes.
Is there any data available from origin spacecraft, your origin spacecraft?
Yes, sir. It's there is a website, Cassini website under NASA. There they simply upload all these data available. Anyone can just download and then do data analysis.
But did you check your result with the Horizons data?
No yet, sir. No. Because this one, as I said, we're more interested in what has been done and what are the defects, and then how to improve those models. That is our concentration so far. So later on, maybe you can ask us, you can confirm it.
Yes, any more questions? So, is the physics of your magnetic pole strength variation with time per year, on the order of nano Tesla per year, right? So, is the physics known?
Yes, sir. This The analysis simply is the Lorentz or the whether we use spherical harmonic, but in the case of rotating, we need to use spherical harmonic coordinates. That is known. The equations are there. How we study this charged particle motion. We can.
So that is your multipolar expansion. Out of that, your dipole, quadrupole, and that higher order octapole.
Yes.
No, only these are the significant. Out of that, only the last pole, what you mentioned, quadrupole, that varies more significantly than the rest of the poles. I am interested in the basic physics behind where there is significant annual increment or annual variation of this pole, quadrupole moment.
No, sir. That is still unopened question, sir.
Unknown.
Yes, unknown because we don't know what is going in the inside. Like the Stevenson proposal, it's not yet confirmed. So that's still an open question.
Okay, thank you. If there is no more question, let us thank the speaker once more.
Sir, I have a question.
Oh, one more question.
Yes.
New question, please.
So, like, it has a magnetic field. So, do we see like northern and southern lights like in Jupiter or Earth?
Yes, it is. We call aurora. Okay,
Yeah.
and in fact, on top of the Saturn, we call something hexagon.
Yeah.
Hexagon, which is almost even the size of the planet.
Yeah.
Our planet. There is the wind circulating hurricane.
Yes.
Those things are there. Yes.
So those hexagonal artifacts, they are due
Yes.
to the magnetic field in that region.
That also is expected to create because any movement of the charge will create magnetic field. That is expected. But now, how does it affect? See, that's why I call it internal magnetic field.
Yes.
Now, if I'm considering the magnetic effect of that one, it becomes the external contribution of the magnetic field. Okay, so that has nothing to do with the origin of the planet. So that they are there. In fact, there is something called ring current because the charged particle group and then it creates a current and that creates again azimuthal magnetic field. So they are outside. If you are considering outside, there are so many magnetic fields.
Yes. Yes.
Okay, we did not consider that.
Okay, thank you. The next speaker is Amon Lamchengbi Chanu. Okay, title is Spectral Study of X-ray Sources in 12 Galaxies Recently Observed by Chandra.
Good afternoon, everyone. I'm Amon Lanchenvi Chanu, and working under the supervision of Dr. A. Senorita Devi. I have just completed my coursework last month. So, in this presentation, I will try to incorporate everything what I have done in this 1 month after the coursework. So, my topic is spectral study of X-ray sources in 11 galaxies recently observed with Chandra. These are the outline of my presentation. So to begin with, X-rays, they are a special class of binaries emitting X-rays which consist of a normal star or a dwarf star accreting their mass onto a compact object, which can be either a neutron star or a black hole, and they have their luminosities greater than or equal to 10 to the power 38 arcs per second. While the ultra-luminous X-ray sources, they are generally bright point-like non-nuclear extragalactic sources with luminosities around 10 to the power 39, or they may even reach up to 10 to the power 42 arcs per second. So for my observation, I have downloaded the data that were available in the public data archive of Chandra X-ray Center from the year 2020 to 2022. The galaxies that are considered were observed with SCs, and the X-ray sources were often from 11 galaxies. So these are the sample properties of the sample galaxies that are considered. The distances of the galaxies were taken from the NASA extragalactic database, and the exposure of the sources are given in this column, and while this is the public release date of the galaxies. So for the data analysis, I have used the Chandra Interactive Analysis of Observation, Xiao. With the Xiao tool web detect, which were run in 2 phases, W transform and WRECON, I have extracted the X-ray point sources from the event tool list. Here, this is the event tool file from where the sources are sources and the backgrounds are extracted. So I have often 31 sources from this total of 11 galaxies. So with using the spec extract, the spectrum of the sources are generated, and using XSpec, which is a spectral fitting package, I have fitted the spectrum with two models, the absorbed Dix blackbody model and the absorbed power law model in the energy range 0.3 to 8 keV. And these are some more. As there are 31 sources, I cannot include all of these spectra. So I have just chosen 3 of the galaxies. So these are the spectrum of the sources plotted by Dix blackbody model and the power law model. And so this is the spectral parameters of the sources. I would focus only on the galaxy or on the source NGC 5194 or Messier 51. It was observed. It has 4 observation IDs. Out of these 4 observation IDs, I have got 7 sources, and these are the inner Dix temperature of the sources that were extracted, that I have got using the Dix blackbody model. And this is the log of the luminosity that I have calculated, and while this is the reduced C state. Similarly, this is the photon index gamma plotted by the power law model, and this is the log of the luminosity, and this is the reduced C state. The table continues for all the 31 sources, and from this, from all the 31 sources, out of the all 31 sources, within the uncertainty limits, I have often, there are 25 sources of the order with their luminosity is greater than or equal to 10 to the power 40 hours per second in the energy range of 0.3 to 8 kilo electron volt. So these sources, these 25 sources, they fall in the range of ultraluminous X-rays. And out of the 31 sources, 6 of them have the luminosity around 10 to the power 38 hours per second. So they are in the X-ray binaries range. And out of the 25 ULX, I have got the 23 are in the hard, spectrally hard, with inner Dix temperature in the range of 0.73 to 2.8 keV when fitted by the Dix blackbody model, and 2 of the ULX are soft with inner Dix temperature around 0.47 keV and 0.57 keV plotted by the Dix blackbody model. So from this I conclude that the spectrum of the soft sources, they may be explained by emission from accretion Dix, while that of the hard sources may be explained by the inverse Comptonization of soft photons. That's all. These are the references that I have used.
Okay, thank you for your nice presentation. It's now open for discussion. Any question?
What kind of galaxies they are?
There are nearby galaxies. Only a few of them are extragalactic.
No, that's fine. I'm asking about the types of the galaxies. Are they irregular kind or ellipticals or dwarf galaxies or
It's a mixture, I would say. I've randomly picked the galaxies that were released in during the year 2020 to 2020.
normally, right?
Okay, yes.
I'm just wondering that from your analysis, so you said these are like ultra-luminous sources. So, and you said this can be only like binary systems. So, is it possible from your analysis to know what kind of binaries these are? Maybe they're, they're black hole binaries or like they're neutron star binaries. What kind of, is it possible to get the information?
Sorry.
Yes, please ask.
So in the NMX, so generally it is believed that the central echo that is implemented
could not hear you.
Okay, just.
Be audible.
So generally in case of ULX, the central black hole, or in case of black hole, it is believed that it is an intermediate mass black hole, right? So do you think that there is any possibility that the black hole can be a stellar mass black hole? With that accretion rate, can we get this amount of luminosity? I mean, greater than 10 to the power 40 ounce per second.
Yeah, if we consider it to be an isotropic emission, we can calculate the black hole mass of these sources. So after calculation, if we get the mass of the black holes in the stellar range, or if it is beyond the stellar range, we can classify them as intermediate mass black holes. It is greater than around.
It is already believed that it is an intermediate mass black hole. So I am asking about what is the possibility that that black hole can be a stellar mass black hole, which will produce this amount of luminosity.
I'm sorry.
Okay. If there is no more, let us thank the speaker once more. Now the next speaker is S. Johnson Singh, and title of discussion is Area Spectrum of Non-Rotating Big-Jet Black Hole.
Good afternoon, everyone. I am Saiful Johnson, and I am doing research under the supervision of Dr. Irom Abdul Maitei, and the title of my presentation is Area Spectrum of Non-Rotating BTZ Black Hole. Introduction. For the first time, Einstein proposed that the horizon area of black hole is equally space discrete that is quantized, and later on many researchers studied the area spectrum of black holes, and among these studies, some of the studies are shown in this slide. And they studied area spectrum of black hole for different space-time by using different methods. Among these studies, some of the studies are Hood studies the spacing of horizon area using polynomial modes and Bohr correspondence principle. And by using quantum loop gravity, Dyer studies the area spectrum of black hole. And from the commutation, radiation, and condensation condition of angular momentum, Lopotenko also showed that the black hole area is quantized. In our research work, we will study the area and entropy spectrum of non-rotating BTZ black hole by using adiabatic invariant quantity and the first law of black hole thermodynamics. And for this, we consider a non-rotating BTZ black hole. And the line element of this black hole is given by this equation number 1. And here delta R is equal to minus m plus r square by l square. And from this line element we extracted very useful parameters such as the location of event horizon, surface gravity, and the temperature at event horizon. And they are given by this equation number 3, 4, and 5. And for a black hole, this adiabatic invariant quantity is given by this expression, that is integration of pi dqi. And using Hamilton's path equation of motion, this pi is written in the form of Hamiltonian h. And here in this expression, tau is the proper time, and the factor 2 comes out after doing summation over I indices. And we write this expression in the form of this equation of number 6. If we do cancellation, we will get this equation from this equation. And here Rn and Rout are the location of event horizon when the particle turns out, and R dot is the radial outgoing path when the particle turns out. And the first metric is equidistant by using this transformation, and we get this matrix. And from this matrix we calculate the radial null part, that is R dot, and we found the region as shown in this slide. And here plus sign represent the radian outgoing part and negative sign represent the radian ingoing part, null part. And the value or dot is put in the equation number 6 here, and we find this expression, and we perform for the integration with respect to R by using contour integration, and from this, after doing contour integration, we get this expression, and the value of K surface gravity is put here, and here we use first law of black hole thermodynamics, and finally we get this result, that is S cut and S. And for more Sommerfeld quantization rule, we have this relation, and we compare equation number 9 with 10, and after doing this comparison, we get the expression for entropy. That is S is equal to twice pi n, and the spacing between the nearing values of n are calculated and is shown in equation number 12. And spacing between entropy spectrum is found to be twice pi. And we know that entropy is equal to area by 4 LP square, where LP is the Planck length. When we put this value in this equation number 12, we found the spacing of area spectrum. And finally, I get the result. The spacing between the entropy spectrum is found to be twice pi, and the spacing between area spectrum is found to be at pi LP square. And in this region, we know that both entropy spectrum and area spectrum are discrete equally spaced, that is quantized. And from this region, it is also known that this spacing between entropy spectrum and area spectrum is independent of black hole parameters. And our region is in agreement with Wittgenstein original region, but it differs from the region calculated using Quasi-Neumann modes. In near future, I will do research on Quasi-Neumann modes under the supervision of my supervisor, Dr. Irong Oblu-Mete. And these are my references, and thank you.
So thank you for your interesting presentation. The session is now open for questions and answers. Any question?
Yes, sir.
This area quantization,
Ah.
who did that? That Wittgenstein?
First, Wittgenstein proposed that,
Okay.
and then later on, many researchers studied the area spectrum of different black holes using different methods. Some of the studies are shown in this point number 3,
Yeah,
4,
I agree.
5.
No, what I'm saying is the quantization of area is somehow connected to loop quantum gravity. Did you check that one?
Yes. Right now, I haven't checked this,
Yeah.
but I found this Dyer studied using quantum loop gravity.
Yeah. So that you can have a check.
Yes, I will check it in near future.
Okay, any more questions? Yes, please go ahead.
Can you go to slide number 6?
That number 6. This one.
Yeah. So, I'm sorry I told you about that. So, why did you take the transformation P tends to I tau? So, why? Is there any motivation?
Here, our aim is to study this curved space-time into plane space-time. Actually, time t is physically time that we observe in standard physics relation, and we, in order to make easier mathematically, in order to treat it as a coordinate, we introduce this transformation.
Yes, any more questions? If no, Let us thank the speaker once more. Now this is the last invited talk of the last session. Okay, going to be deliberated by Ablu Maiti, and title is Hawking Radiation and Thermodynamics of Schwarzschild, a black hole surrounded by quintessence. Okay.
Good afternoon. Due to the time constraints, I won't be taking much time. I'll try to finish as quickly as possible. So my topic is Hawking radiation and thermodynamics of Schwarzschild black hole surrounded by quintessence. The motivation of the work, of the present work, motivation of the present work is that we found two different different ideas about the black hole remnants, of Schwarzschild black hole surrounded by quintessence. And the first one is by M.D. Sehzal, which shows that this Schwarzschild black hole surrounded by quintessence with the quintessence parameter omega q is equal to minus 2/3 evaporates completely. Whereas another paper, Islamzadeh and Nozari, they showed both in the nuclear physics B, both showed that the black hole cannot evaporate completely. So there is to be a black hole remnant with non-zero mass would be formed. So just to correlate these two, whether this which one is true, we just wanted to observe, and this is the motivation of the theory, motivation of our work, and this the importance of the black hole remnant is quite well known, and these black hole remnants are candidates for the pole dark matter, and whether this and whether these black hole remnants are formed or not. Okay, that we wanted to test. And so for that we take the line element of the Schwarzschild black hole surrounded by quintessence given by these equations, and then what we did, we calculated, we considered the tunneling of the scalar particles, and we also incorporated quantum gravity effects by using the generalized Klein-Gordon equation, and we took a wave function of the scalar particle of this form, and then when we substituted in the generalized Klein-Gordon equation, we find the Hamilton-Jacobi equation given by this, and then in order to solve this Hamilton-Jacobi equation, we use a separation of variables, and then the radial part is given by this equation. And there are two physically meaningful solutions given here, and considering this omega q of minus 2/3, then we solved it, and then from the tunneling probability we found the Hawking temperature given by this expression, and then we also determined the entropy of the black hole, and then the heat capacity of the black hole is given by this expression. So when we plotted this heat capacity, and it is for this particular value of minus 2/3, it is this one. It is this one. Omega Q is equal to 2 by minus 2/3. It is this one. So according to Adler, when the heat capacity vanishes, there is a formation of the black hole remnant, and the mass of the remnant formed is given by that particular value of the mass. And here we are plotting the mass along the x-axis, and along the y-axis the heat capacity is plotted. So from this graph, here there are 2 points where the heat capacity vanishes. So if for those black holes whose conditions are such that it is here. If the black holes are satisfied this region, then they will form remnants with non-zero mass, non-zero remnant mass. And whereas if the black holes satisfy this condition, and if the black hole is in this region, then the zero remnant, no remnant will be formed, and it will be completely evaporate. So this is so our result. This is our result. Unifies the two results. There were the two opposite results that were that I just discussed, and this is and what is important is the condition. What is important is the condition of the black hole. It should be the conditions like mass and this quantity A, and in this way we unify the two opposite results. Thank you. Is there any question?
Thank you for nice presentation. It's now open for discussion. So question?
Yes.
Yes.
So can you just simplify this range of this special heat from positive to negative?
Which one?
Signifies that these negative and positive special heat.
Positive and negative heat capacity. So from the basic physics, so the heat capacity is the amount of heat required to increase the temperature by 1 degree. So if it is negative, so it shows that if we extract it radiates, the temperature will increase, and we don't have to give more heat. And as it radiates, its heat capacity keeps as it radiates, its temperature keeps on increasing. And whereas for the positive one, we have to supply heat. The input should be positive input should be given.
So it is related to the entropy. In one case, entropy is increasing, in another case, entropy is decreasing.
Yes.
So, but in universe, it states that the second of thermodynamics says that entropy should always increase. So how do you justify this decreasing entropy?
Decreasing
Entropy.
entropy. Okay, for that we have to check. We have to see the entropy, the expression for the entropy. Okay. So you mean to say that is the no, this negative heat capacities, it is also, it may not mean this one decrease in the entropy. It may not necessarily be interpreted as the decrease in entropy. It is also this negative heat energy, negative heat capacity is also observed. It is also observed, especially during the especially in stars. There will be periods when we have negative heat capacity, maybe negative. So it may not mean that the entropy is always decreasing.
So it's like we're talking about local change.
Yes, yes, not local change. It may not be interpreted as decrease in the entropy.
Is there any more question? If no more, let us thank the speaker once more. Okay, thank you. So in this session, we had 9 talks.